The actual orientation of the sensors when the measurements are taken isn't actually that important for the math. What's important is knowing how much the orientation has changed from one measurement to the next. And so the way we do that, the first way is we use this cube that's laser cut, so it's very precise, the measurements of all these pieces of plastic. So it's very square, and it's designed to go together in a way that makes it as square as possible. So that's the first way. And then the second way is we have this Technic servo motor. Technic is a company that makes really excellent servo motors. I just looked it up. The repeatability for this motor is 1/100th of a degree, and the resolution on the encoder is about the same. And so that's way more precise than we need. And then we have this. The servo motor is coupled with this long aluminum shaft. We use a very thick shaft, so it's rigid. But we have it be 1 meter long, so there's a bunch of magnetic stuff going on in the servo motor. We don't want that affecting the magnetic field that the sensors see. And so we have this set up so that there's no ferrous metals near the sensor. And what that means is that the magnetic field in this area is constant. So it's not going to be unaffected by, like, we have a lot of metal shelving and stuff around here that does influence the field in this region, but as long as that stuff is far away, the influence it has in this region doesn't change in space. So if I move like 1 centimeter in one direction or the other, the magnetic field doesn't change. And so that means that as we tumble the device around in this cube, the magnetic field in this area that the sensors see is the same for every measurement. The only thing that's changed is the orientation, and we know exactly how the orientation has changed because we have this very square cube and a very precise servo motor. So that's how it works, and now we'll do a time lapse showing the actual process happen. So here's a ProStart ready to calibrate. I'm going to snap it into the mounting cradle in the calibration cube there. And then set it here, and I'm going to start the robot. The robot's going to pick it up. And so you'll notice that the robot's going to put the cube on the table and push it in place against those walls at the end of the table. And then the robot retracts and gets as far away from the cube as possible. And that's just so all the electric motors and stuff on the robot are not influencing the magnetic field near the ProStart. And now the turntable goes to 4 precise orientations for this side of the cube facing up. And then once that's finished, the robot's going to go back and flip the cube to another side. And then we'll do the same thing over again. So we're taking 4 measurements for each side of the cube facing up. And then this lets us we have a bunch of measurements of the Earth's gravitational field with the accelerometers on the ProStart, the magnetic field with the magnetometer, and then also each time it does one of these quarter turns, we know that it's moving exactly 90 degrees. And we look at the gyroscope measurements in the ProStart, and we basically measure what the gyroscopes think the rotation is and compare it to what we know it actually was, and that allows us to calibrate the gyroscopes as well. So we're calibrating 3 sensors simultaneously here. Okay, so it's finished that first side, and now the robot's gonna flip the cube over and put it on another side, and then the process keeps going. And now we're going to set up a time lapse so you can see the whole thing